Electric charges are a fundamental property of matter. There are two types: positive charges like protons and negative charges like electrons. Like charges repel each other, while unlike charges attract. The unit of charge is the coulomb. Charge distributions come in various forms. Point charges have 0 dimensions. Line charges have 1 dimension with linear charge density lambda. Surface charges spread in 2 dimensions with surface density sigma. Volume charges fill 3-dimensional space with volume charge density rho. Coulomb's law describes the electrostatic force between charged particles. The force is proportional to the product of charges, inversely proportional to the square of the distance, and acts along the line joining them. The constant Ke equals 1 over 4 pi epsilon 0, approximately 8.99 times 10 to the 9 Newton meter squared per coulomb squared. The electric field is a vector quantity that represents the force per unit charge at a point in space. For a point charge, the electric field points radially outward for positive charges and inward for negative charges. Its magnitude decreases with the square of the distance from the charge. The electric field has units of newtons per coulomb or volts per meter. For continuous charge distributions, we calculate the electric field by integrating the contributions from infinitesimal charge elements. For a line charge with density lambda, we integrate along the length. For a surface charge with density sigma, we integrate over the area. For a volume charge with density rho, we integrate throughout the volume. The process involves breaking down the distribution, finding the field from each element, and then integrating. Electric field lines provide a visual representation of the electric field. They start from positive charges and end at negative charges. The density of field lines indicates the field strength. Field lines are always tangent to the electric field vector at every point and never cross each other, as the electric field has a unique direction at each point in space. Electric potential is a scalar quantity defined as the potential energy per unit charge. For a point charge, it equals Ke times Q divided by R. Unlike the electric field, which decreases as 1 over R squared, potential decreases as 1 over R. The unit of potential is joules per coulomb, or volts. Electric potential is a scalar, can be positive or negative, and is defined up to an additive constant. The electric field is the negative gradient of the electric potential. For spherically symmetric systems, this simplifies to negative dV dr times the unit radial vector. Electric field lines are perpendicular to equipotential surfaces, always pointing from higher to lower potential. The field strength is greater where equipotential surfaces are closer together. Symmetry plays a crucial role in electrostatics. Spherical symmetry occurs when the charge distribution is spherically symmetric, like point charges. Cylindrical symmetry appears in systems like line charges and charged cylinders. Planar symmetry is found in infinite charged planes. These symmetries simplify our calculations by reducing 3-dimensional problems to 1 or 2 dimensions and make tools like Gauss's law more applicable. Gauss's theorem states that the electric flux through a closed surface equals the enclosed charge divided by epsilon 0. The electric flux measures the number of electric field lines passing through a surface. For a positive charge, the field lines point outward, creating positive flux. Gauss's law provides a powerful method for calculating electric fields when symmetry is present. Gauss's law is particularly useful for calculating electric fields of symmetric charge distributions. For a point charge, using a spherical Gaussian surface gives us Coulomb's law. E equals Q over 4 pi epsilon 0 R squared. For an infinite line charge,